Imagine a world where particles can be in two places at once, where reality itself depends on whether you're looking at it, and where the very fabric of space whispers secrets that defy logic. Welcome to the bizarre realm of quantum mechanics, where the rules of our everyday universe don't just bend, they shatter. If you think outer space is mysterious, wait until you peer into the subatomic playground that makes up everything around us. Scientists have spent decades trying to unravel these quantum puzzles, and yet, the deeper we dig, the stranger it gets. Today, we're diving into 30 mind-blowing quantum mysteries that could hold the keys to explaining the universe itself. From particles that vanish and reappear across barriers to the eerie connections that span galaxies in an instant, these aren't just theories, they're the cosmic riddles rewriting the story of reality. And here's the wildest part: the more we uncover, the less we seem to understand. So, buckle up. By the end of this journey, your view of the universe might never be the same. Now, let's step into our first quantum mystery, one that flips everything we thought we knew about the building blocks of reality. Picture this: tiny particles like electrons don't just behave as solid little dots. They also act like waves, spreading out and interfering with themselves. This bizarre duality is called wave-particle duality, and it's the kind of head-scratcher that makes quantum mechanics so fascinating. The classic experiment that revealed this madness is the double-slit experiment. Here's how it works. Imagine shooting tiny particles like electrons, one by one, at a barrier with two narrow slits. If electrons were just particles, you'd expect them to go through one slit or the other and leave two neat piles on the other side. But that's not what happens. Instead, they create an interference pattern, like ripples in a pond, as if they're waves passing through both slits at once and overlapping. Even weirder, if you try to peek and see which slit each electron goes through, the interference pattern vanishes and they act like plain old particles again. It's almost as if the electrons know they're being watched. This experiment isn't just a quirky lab result, it's a fundamental puzzle. It tells us that particles don't have definite states until we measure them. They exist in a blurred mix of possibilities, a concept that blows apart our everyday intuition about how objects should behave. Wave-particle duality isn't just some abstract idea. It's the foundation of technologies like electron microscopes and even quantum computing. Yet, even after decades, scientists still argue over what it really means. Is reality just a collection of probabilities waiting to snap into place? The answer might rewrite physics itself. And here's the kicker: this isn't just about tiny particles. Some researchers believe that if we could scale up the experiment, even objects as big as a baseball could, in theory, show wave-like behavior. The universe, it seems, is far stranger than we ever imagined. Now, let's unravel another mind-bending mystery that takes the weirdness of quantum mechanics even further. If you thought wave-particle duality was strange, wait until you hear about quantum superposition. The idea that particles can exist in multiple states at the same time until someone or something measures them. To wrap your head around this, imagine Schrödinger's famous cat. The thought experiment goes like this. A cat is placed in a box with a tiny bit of radioactive material, a Geiger counter, and a vial of poison. If the radioactive atom decays, the Geiger counter triggers, releasing the poison and killing the cat. But here's the twist: according to quantum mechanics, until you open the box and look inside, the radioactive atom is in a superposition, both decayed and not decayed at the same time. That means the cat is, in a way, simultaneously alive and dead. Sounds impossible, right? Yet this is exactly how tiny particles behave in the quantum world. Superposition isn't just a bizarre hypothetical, it's been confirmed in real experiments. Take an electron spin, for example. Before measurement, it doesn't have a definite spin direction. It exists in a blur of all possible spins. Only when we observe it does it snap into one state. This flips classical physics on its head, where objects have defined properties at all times. In the quantum realm, reality is more like a mirage of possibilities. This concept isn't just philosophical, it's the backbone of quantum computing. While classical computers use bits that are either 0 or 1, quantum bits or qubits exploit superposition to be both 0 and 1 simultaneously. That's why quantum computers could solve certain problems exponentially faster. But here's the catch: the moment you measure a qubit, its superposition collapses and you lose that quantum advantage. So, what does superposition tell us about reality? It suggests that the universe at its most fundamental level doesn't operate on solid, predictable rules. Instead, it's a tapestry of probabilities where observation itself shapes what's real. It's a mystery that challenges not just physics, but our very understanding of existence. And if that doesn't make you pause, just wait, the next quantum mystery might bend your mind even further. Now, let's step into one of the most baffling corners of quantum physics: quantum entanglement. Albert Einstein famously called it spooky action at a distance. And once you understand why, you'll see exactly what spooked him. Imagine two particles becoming entangled, meaning their properties are linked no matter how far apart they are. Change one and the other instantly changes two, even if they're on opposite ends of the universe. Here's the wild part: this connection happens faster than light, which should be impossible according to Einstein's theory of relativity. Relativity says nothing can travel faster than light, not even information, but entanglement defies that. It's as if the particles share a hidden language, communicating in a way that doesn't rely on distance or time. Experiments have confirmed this, showing that measuring one entangled particle immediately determines the state of its partner, no matter how far apart they are. So how does this work? The truth is, we don't fully know. Some theories suggest entangled particles aren't truly separate but part of a deeper, interconnected reality. Others argue that their connection happens through hidden dimensions or some yet undiscovered physics. What we do know is that entanglement isn't just a lab curiosity. It's the foundation of groundbreaking technologies like quantum communication and quantum cryptography. Imagine sending a message that can't be intercepted because any attempt to spy on it would instantly alter the entangled particles, alerting the sender and receiver. This could revolutionize secure communication, from military operations to online banking. But entanglement also forces us to rethink relativity. If information can somehow bypass the speed of light, does that mean our understanding of space-time is incomplete? This mystery doesn't just challenge physics, it shakes the very framework of how we perceive reality. Are entangled particles revealing a hidden layer of the universe, or is there something even stranger at play? One thing's certain: the deeper we dig into quantum mechanics, the more it feels like we're peeling back the curtain on a reality far beyond our everyday experience. And if you think entanglement is mind-bending, just wait until we explore the next quantum puzzle. Just when you thought quantum mechanics couldn't get any weirder, here comes the measurement problem, a mystery so profound it makes even physicists scratch their heads. Picture this: a quantum particle can exist in multiple states at once, like Schrödinger's cat being both alive and dead. But the moment you measure it, that superposition collapses into a single, definite state. Why? That's the million-dollar question. The classic explanation comes from the Copenhagen interpretation, which says the act of observation forces the quantum system to choose a state. But here's the twist: it doesn't specify what counts as an observer. Is it a conscious human, a machine, the universe itself? This vagueness has sparked debates for decades. Some physicists argue that consciousness plays a role, suggesting reality might not fully exist until it's observed. Others reject this idea entirely, proposing that the collapse happens through interactions with the environment, not conscious minds. Then there's the many worlds interpretation, which sidesteps the problem entirely by suggesting every possible outcome does happen. just in alternate universes. No collapse, just an ever-branching multiverse. But even this raises questions. If every possibility becomes real, where's the line between what we measure and what's out there? The measurement problem isn't just philosophical, it's practical. Quantum computers rely on superposition to perform calculations, but the moment you read their results, those delicate states vanish. Understanding why could unlock even more powerful technologies. So, is reality shaped by observation, or is there a deeper mechanism at work? Until we solve this puzzle, one thing's clear: the quantum world refuses to play by the rules we expect. And speaking of rules, our next mystery dives into how particles pull off impossible escapes. Welcome to the enigma of quantum tunneling. Now, let's step into the realm of the downright impossible, or at least what should be impossible. Quantum tunneling is like the ultimate magic trick of the subatomic world. Imagine a ball rolling toward a hill. In the classical world, if the ball doesn't have enough energy to climb over the hill, it just stops. But in quantum mechanics, that particle doesn't care about your hills. It can vanish on one side and reappear on the other, as if the barrier isn't even there. How does this happen? Blame the wave-like nature of quantum particles. Their position isn't a single point but a spread-out probability cloud. There's always a tiny chance, however small, that the particle's wave function leaks through the barrier, allowing it to pop out on the other side. It's not teleportation in the sci-fi sense. It's more like a statistical sneeze where the particle defies the odds. And here's where it gets real. Quantum tunneling isn't just a lab curiosity. It's the reason your electronics work. Transistors in chips rely on tunneling to function at nanoscales, and without it, modern computers wouldn't exist. Even the sun owes its shine to tunneling. In its core, protons that should repel each other due to their positive charges instead tunnel through the energy barrier, fusing into helium and releasing the light that powers life on Earth. But the wildest part, tunneling might hold the key to fusion energy here on our planet. If we can harness it more efficiently, we could unlock near-limitless clean power. So while tunneling shatters classical intuition, it's also one of quantum mechanics' most practical and universe-shaping miracles. And if you think that's bizarre, wait until we explore the uncertainty principle, where quantum particles refuse to even tell us their full story. Now let's tackle something even more mind-bending: the uncertainty principle. A rule so fundamental it reshaped our understanding of reality itself. Picture this: you're trying to measure a tiny particle's position and momentum, like tracking a speeding bullet. In the classical world, you'd expect to pin down both with perfect accuracy. But in quantum mechanics, the universe straight up says no. Heisenberg's uncertainty principle tells us there's a built-in limit to how precisely we can know certain pairs of properties, like a particle's position and momentum. The more accurately you measure one, the fuzzier the other becomes. It's not a flaw in our tools, it's a cosmic rule written into the fabric of reality. Blame the wave-particle duality again. A particle's position is tied to its wave-like spread, and its momentum depends on the wavelength. Sharpen one, and the other inevitably blurs. This isn't just a quirk of measurement, it shreds the classical idea of determinism, the belief that if we knew every particle's position and momentum, we could predict the future with absolute certainty. Quantum mechanics, with its uncertainty principle, replaces that clockwork universe with one built on probabilities. Einstein famously hated this, insisting, "God does not play dice," but experiments keep proving Heisenberg right. What does this mean for us? It rewires our philosophical foundations. If the universe operates on uncertainty at its core, then absolute predictability is an illusion. Every quantum event carries a whisper of randomness, shaping everything from chemical reactions to the stars. So next time someone claims they have life all figured out, remember, even the universe keeps its options open. And speaking of open questions, let's dive into how quantum systems lose their weirdness when they meet the everyday world, the puzzle of quantum decoherence. Now, let's unravel why the quantum strangeness we've been exploring doesn't play out in our everyday world. This brings us to quantum decoherence, the process that tames the wild quantum realm into the familiar classical reality we know. Imagine a quantum particle, like an electron, happily existing in a superposition of multiple states until it bumps into its environment. Every air molecule, photon, or even stray bit of heat acts like a tiny observer, constantly nudging the particle. These interactions aren't gentle. They force the particle to pick a single state, collapsing its quantum weirdness into something definite. This is decoherence in action, the reason Schrödinger's cat is never both alive and dead in your living room. The key here is scale. In isolated labs, scientists shield quantum systems from these disruptive interactions to preserve their coherence. But out here, the world is noisy. A single dust particle carries trillions of atoms, each jostling anything quantum-sized into classical submission. Decoherence happens staggeringly fast, often in fractions of a second, which is why we don't see quantum superpositions in everyday objects. Try putting a baseball in two places at once, and decoherence slams it into one position before you can blink. But here's the twist: decoherence doesn't just erase quantum effects. It explains why we perceive a single, stable reality. The universe isn't magically switching between quantum and classical rules. Instead, decoherence reveals how classical reality emerges from quantum foundations when systems get too big or too tangled with their surroundings. It's the missing link between the probabilistic quantum world and the predictable one we experience. So next time you wonder why tables don't teleport or why your coffee stays in its cup, thank decoherence, the unsung referee keeping quantum chaos in check. And speaking of chaos, let's turn to a phenomenon where observation doesn't just disturb a system but freezes it entirely: the quantum Zeno effect. Now, let's dive into a quantum quirk where watching too closely can literally stop time for a particle: the quantum Zeno effect. Named after the ancient Greek philosopher Zeno's paradox, where a flying arrow is frozen in time if you observe it at every instant. This effect shows how relentless measurement can halt a quantum system's evolution. Here's how it works. In the quantum world, particles don't change state smoothly. They do it probabilistically, like flipping a coin. But if you keep checking the coin mid-flip, you interrupt its natural progression. Frequent observations reset the system's quantum clock, effectively freezing it in its initial state. Think of it like a toddler constantly asking, "Are we there yet?" On a road trip, the interruptions prevent you from ever reaching the destination. This isn't just theoretical. Labs have demonstrated the Zeno effect by bombarding unstable particles with rapid measurements, slowing their decay. It's as if the particles under surveillance cling to their original form out of quantum stage fright. But there's a flip side, the anti-Zeno effect, where too much observation can actually speed up changes, like badgering that same toddler into sprinting forward. The paradoxes don't end there. The Zeno effect blurs the line between observer and participant, suggesting that watching isn't passive, it's an active force shaping reality. This has wild implications for quantum computing, where preserving fragile quantum states is crucial. By strategically applying the Zeno effect, scientists could freeze qubits in their desired states, shielding them from errors that would otherwise wreck calculations. So while the quantum Zeno effect might sound like a parlor trick, it's a profound reminder that in the quantum realm, seeing isn't just believing, it's intervening. And speaking of interventions, let's examine how empty space isn't really empty at all. It's a seething quantum foam where particles pop in and out of existence. That's next. Now let's pull back the curtain on what seems like nothingness, because even empty space is buzzing with quantum activity. Welcome to the strange world of vacuum fluctuations, where so-called empty space is far from empty. It's actually a turbulent sea of virtual particles popping in and out of existence in the blink of an eye. Here's the mind-bending part. According to quantum field theory, space is never truly still. Instead, it's filled with fleeting pairs of particles and antiparticles that emerge from the vacuum, borrow energy briefly, and then annihilate each other almost instantly. This isn't just theoretical, we've seen the effects in action. Take the Casimir effect, where two uncharged metal plates placed incredibly close together in a vacuum are pushed together by the sheer pressure of these virtual particles. Outside the plates, countless particle pairs can form, but between them, only certain wavelengths fit, creating an imbalance that drives the plates together. It's as if the universe's hidden energy is flexing its muscles, but the implications go even deeper. These vacuum fluctuations might hold the key to one of cosmology's biggest puzzles, dark energy. The energy of these virtual particles should, in theory, contribute to the expansion of the universe. But here's the problem. When scientists calculate the predicted energy density of the quantum vacuum, it's off by a factor of 1 followed by 120 zeros. That's the largest discrepancy in science, dubbed the vacuum catastrophe. It suggests we're missing something fundamental about how quantum mechanics and gravity interact. So while vacuum fluctuations might sound like an esoteric quirk, they're at the heart of some of physics' most pressing mysteries. They challenge our understanding of space, energy, and even the fate of the cosmos. And if that's not enough to make you question what's really going on in the empty spaces around us, just wait, because next, we'll explore how Einstein's own challenge to quantum mechanics led to one of its most surprising validations. Now, let's step into a thought experiment that even Einstein found troubling, because sometimes quantum mechanics doesn't just defy intuition, it seems to break the rules of reality itself. This is the EPR paradox, named after Einstein, Podolsky, and Rosen, who used it to challenge quantum theory's completeness back in 1935. Their argument was simple but profound. If quantum mechanics were correct, particles could influence each other instantly across vast distances, violating relativity's cosmic speed limit, the speed of light. Einstein famously called this spooky action at a distance, convinced it revealed a flaw in quantum theory. Here's how the paradox works. Imagine two entangled particles, like electrons, created together so their properties are linked. Measure one's spin, and you instantly know the other's, no matter how far apart they are. Einstein argued this implied hidden variables, unseen properties that predetermine the particle's states, preserving locality, the idea that nothing influences anything faster than light can travel. To him, quantum mechanics was incomplete because it couldn't explain this correlation without resorting to spooky, instantaneous communication. But here's the twist. Decades later, physicist John Bell devised a way to test Einstein's hidden variables against quantum mechanics. His theorems showed that if local realism were true, entangled particles would obey strict statistical limits. Yet, experiment after experiment, starting with Alain Aspect's groundbreaking work in the 1980s, revealed that entangled particles violate these limits. They behave exactly as quantum mechanics predicts, with correlations stronger than any hidden variable theory could allow. So what does this mean? Einstein wasn't entirely wrong to question quantum mechanics, but the universe, it turns out, is even stranger than he imagined. There's no hidden layer of reality preserving locality. Instead, entanglement's spooky connection is real, forcing us to rethink how information and causality work at the quantum level. And while this might sound like abstract physics, it's the foundation for emerging technologies like quantum cryptography and teleportation. But before we jump into those applications, there's another quantum oddity to unpack, one that takes the idea of multiple realities from sci-fi to scientific debate. Stay tuned. Now, let's shift our perspective to a concept so mind-bending that it blurs the line between physics and philosophy. quantum immortality is one of the most controversial ideas to emerge from the many worlds interpretation of quantum mechanics. Imagine this: every time you face a life or death scenario, your consciousness splits into multiple realities, dying in some but surviving in others. In the realities where you live, you'd always perceive yourself as the one who made it, creating the illusion that you're somehow invincible. To grasp this, picture Schrödinger's cat with a dark twist. Instead of a single box where the cat is both alive and dead until observed, the many worlds interpretation says the universe splits, one where the cat survives, another where it doesn't. Now replace the cat with you. If a quantum event could kill you, say a gun triggered by radioactive decay, your experience would only continue in the realities where the gun didn't fire. From your perspective, you'd keep surviving against impossible odds, while countless versions of you perish in parallel worlds you'll never see. This raises eerie questions. Could this explain near-death experiences or the unsettling feeling of cheating death? Some theorists argue it's possible, but critics point out a glaring flaw: quantum immortality isn't testable. You can't observe the versions of yourself that died, and survivors will always, by definition, only remember living. It's a thought experiment that dances on the edge of metaphysics, challenging our understanding of existence itself. Yet, the many worlds interpretation isn't just sci-fi. It's a legitimate, if divisive, solution to the measurement problem in quantum mechanics, suggesting that every quantum decision spawns new universes. Whether or not you buy into quantum immortality, it forces us to confront a staggering idea. Reality might not be a single timeline, but an ever-branching tree of possibilities, with you conscious in every branch where you survive. Up next, we'll explore how this web of realities might not just be theoretical, but could be etched into the very fabric of space and time. Stay curious. Now, let's take a step even deeper into the quantum rabbit hole, where the very fabric of reality might not be what it seems. The holographic principle is a radical idea that suggests our three-dimensional universe, everything we see, touch, and experience, could actually be a two-dimensional projection, like a cosmic hologram. At first glance, that sounds like science fiction, but it's a serious proposal that emerges from the marriage of quantum mechanics and string theory. Here's how it works. Imagine the universe as a giant movie screen. All the information about every star, planet, and particle, everything that happens in the three-dimensional world, is somehow encoded on a two-dimensional surface at the edge of space. Just like a hologram projects a 3D image from a flat surface, the universe itself might operate the same way. This idea was first inspired by black holes, where physicists discovered that the information swallowed by a black hole isn't lost but stored on its event horizon, a two-dimensional boundary. If the holographic principle is true, it would rewrite our understanding of spacetime. Instead of being the fundamental stage of reality, spacetime would be an illusion, a kind of emergent property from deeper quantum interactions happening on a 2D surface. That means the three dimensions we experience could just be a kind of trick of perception. It also has mind-bending implications for gravity, suggesting that even gravity might not be a fundamental force but something that arises from quantum information encoded on this lower dimensional surface. But how could this possibly be tested? Some physicists are looking for evidence in the cosmic microwave background, the afterglow of the Big Bang, searching for subtle patterns that might reveal a pixel-like structure to the universe. Others are exploring quantum computers to simulate how information might project from two dimensions into three. Whether the holographic principle holds up or not, it challenges us to rethink reality in a profound way. If the universe is a hologram, then the very notion of here and there might be far more fluid than we ever imagined. And that brings us to the next mystery: how gravity itself might be entangled with quantum mechanics in ways we're only beginning to grasp. Now, shifting our focus to another colossal puzzle in physics, we arrive at quantum gravity, the seemingly impossible task of merging quantum mechanics with Einstein's theory of general relativity. These two pillars of modern physics work flawlessly in their own domains, but when it comes to the extreme conditions of black holes or the birth of the universe, they clash violently, leaving scientists scrambling for a unified framework. The heart of the problem lies in their fundamental differences. Quantum mechanics governs the tiny world of particles, where probabilities rule and particles can exist in multiple states at once. General relativity, on the other hand, paints a smooth, geometric picture of space-time bending under the weight of matter and energy. But in places where both should apply, like the center of a black hole, their equations break down into nonsense. This is where loop quantum gravity steps in, proposing that space-time isn't smooth but made of tiny, indivisible loops like a woven fabric. These loops create a granular structure at the smallest scales, preventing the infinities that plague traditional theories. Meanwhile, string theory takes a wildly different approach, suggesting that particles aren't points but vibrating strings, and that extra dimensions beyond our familiar four might hold the key to unification. Both theories have their strengths. Loop quantum gravity keeps things firmly rooted in geometry, while string theory offers a way to include all fundamental forces under one mathematical umbrella. Yet neither has delivered definitive proof, leaving physicists debating which path, if either, will finally bridge the gap. What makes this mystery so thrilling is the sheer scale of its implications. Solving quantum gravity wouldn't just tidy up some equations, it could redefine our understanding of reality itself. From the nature of time to the fate of black holes, the answers are waiting in the quantum shadows just beyond our current grasp. And as we inch closer, the next mystery, how black holes handle information, beckons with even deeper questions. Now, let's dive into a cosmic conundrum that even Einstein would find baffling: the black hole information paradox. Imagine throwing a book into a black hole. According to classical physics, that book and all its information would vanish forever, swallowed by the black hole's unfathomable gravity. But here's the problem: quantum mechanics insists that information can never truly be destroyed. So, what happens to it? Does it disappear, or is it somehow preserved? This puzzle took center stage when Stephen Hawking proposed that black holes aren't entirely black. They emit something called Hawking radiation, a slow leakage of energy that causes black holes to evaporate over time. But if the black hole eventually vanishes, where does the information from that book go? Does it evaporate too, violating quantum laws, or does it linger, hidden in the radiation? Some physicists argue the information is preserved, scrambled into Hawking radiation like a cosmic hologram. Others propose wilder ideas like firewalls, intense walls of energy at the black hole's edge that might destroy anything falling in, preserving information in a bizarre way. But firewalls clash with general relativity, which says you shouldn't notice anything unusual as you cross the event horizon. The stakes couldn't be higher. If information is truly lost, it upends quantum theory. If it's preserved, we might need a radical new understanding of spacetime itself. Either way, solving this paradox could reveal how the universe handles its deepest secrets and whether reality itself is as stable as we think. And as we wrestle with this mystery, another intriguing question emerges. Could time itself be a quantum illusion? But that's a puzzle for another moment. Let's take a moment to question something we often take for granted: time itself. What if time isn't the steady, unchanging river we perceive, but something far stranger, emerging from the quantum realm? This is the heart of Quantum Mystery 15, the idea that time might not be fundamental at all. Instead, it could arise from the interactions of quantum particles, like a cosmic illusion woven into the fabric of reality. Picture the universe at its smallest scales, where particles flicker in and out of existence, entangled and dancing in ways that defy classical intuition. Some theories suggest that what we experience as time is just a side effect of these quantum interactions, a kind of collective mirage. One of the boldest ideas comes from the Wheeler-DeWitt equation, which attempts to unify quantum mechanics with gravity. Strikingly, this equation describes a universe where time doesn't appear at all, suggesting it might be an emergent property, not a fundamental one. Then there's quantum causality, which reimagines cause and effect in a timeless quantum landscape. Could events be connected in ways that don't rely on a linear flow of time? Experiments with entangled particles already hint at connections that transcend classical notions of before and after. If time is truly emergent, it would reshape everything from how we understand aging to the very origins of the cosmos. Yet the mystery deepens. If time isn't fundamental, why does it feel so real to us? Why does the arrow of time always point forward? Some physicists propose that quantum decoherence, the process that makes quantum weirdness fade into classical behavior, might also explain why time seems to flow in one direction. Others wonder if multiple timelines could branch at every quantum decision hidden from our perception. What's certain is this: unraveling quantum time could upend our understanding of existence itself. And as we ponder whether time is real or just a quantum trick, another enigma calls one that bridges the gap between mind and matter, but that's a story for another moment. Now let's venture into one of the most provocative frontiers of quantum mysteries, where the boundaries of physics meet the enigma of human consciousness. Quantum Mystery 16 takes us inside the brain itself, asking a daring question. Could our thoughts, our awareness, even our sense of self arise from quantum processes dancing within the tiny structures of our neurons? At the heart of this idea is the Orch or theory, proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. They suggest that consciousness isn't just the result of classical brain activity, but something far more exotic. Quantum vibrations happening in microtubules, the minuscule protein structures inside our brain cells. These vibrations, they argue, could collapse into definite states through a process akin to quantum gravity, giving rise to moments of conscious experience. But here's where the controversy ignites. Many scientists push back, pointing out that the brain is a warm, wet, and noisy place, conditions thought to destroy delicate quantum effects almost instantly. Critics argue that quantum coherence, the fragile state allowing particles to exist in multiple states at once, would be impossible to maintain in such an environment. Yet, Penrose and Hameroff counter that microtubules might be uniquely shielded, acting as tiny quantum computers orchestrating our very awareness. The debate grows even thornier when we consider what's at stake. If consciousness does have quantum origins, it could redefine everything from artificial intelligence to our understanding of free will. But without definitive experimental proof, the theory remains in the realm of fascinating speculation. Some researchers point to studies on anesthesia, which seems to selectively target microtubules, as potential clues, while others dismiss these as coincidental. Whether the quantum brain hypothesis holds water or not, it forces us to confront profound questions. Are we just classical machines, or is there something quantum woven into the fabric of our minds? As we wrestle with these ideas, another mystery beckons, one that takes us beyond biology and into the strange world of exotic particles. But we'll save that revelation for the next chapter. Shifting gears from the mysteries of the mind to the marvels of matter, let's explore a quantum phenomenon that sounds like it's straight out of science fiction: topological quantum states. Here, particles don't just behave oddly, they defy conventional physics in ways that could revolutionize technology. At the center of this mystery are enyons, exotic entities that exist only in 2 dimensions and possess bizarre properties unlike anything in our 3-dimensional world. Enyons are special because their quantum states depend not just on their position, but on the specific paths they take around each other, like dancers whose moves change the entire performance. This property, called topological order, makes them incredibly robust against disturbances. Imagine a knot that stays tied no matter how you jostle it. That's the kind of stability onions offer, making them ideal candidates for error-resistant quantum computers. Traditional quantum bits or qubits are notoriously fragile, easily disrupted by heat or electromagnetic noise. But topological qubits built from onions could maintain their coherence far longer, potentially unlocking the full power of quantum computing. This isn't just theoretical. The groundbreaking work on topological phases of matter earned physicists David Thouless, Duncan Haldane, and Michael Kosterlitz the Nobel Prize in 2016. Their research showed how these exotic states arise in certain materials, opening the door to real-world applications. Laboratories are now racing to engineer materials hosting onions, with companies like Microsoft betting big on topological quantum computing as the future of the field. Yet challenges remain. Detecting and manipulating onions requires extreme conditions like temperatures near absolute zero and ultra-pure materials. Some skeptics question whether the technology can scale beyond lab experiments. But if successful, topological quantum computing could solve problems deemed impossible today, from designing new medicines to cracking unbreakable codes. As we marvel at these strange particles, another quantum mystery looms, one that tackles how reality itself might emerge from quantum chaos. But that's a puzzle for the next chapter. Now let's turn our attention to one of the most intriguing ideas in quantum theory: how the quantum world decides what becomes real to us. This is where quantum Darwinism comes in, a concept that helps bridge the gap between the fuzzy quantum realm and the solid, everyday reality we experience. At its core, quantum Darwinism suggests that not all quantum information survives the transition to the classical world. Instead, certain states are selected because they're the most stable and reproducible, like how only the fittest traits survive in biological evolution. When a quantum system interacts with its environment, countless tiny interactions act as a kind of natural selection, amplifying some information while letting others fade away. The result, the information that sticks around, becomes what we perceive as classical reality. This idea tackles the infamous measurement problem: why observation seems to force a quantum system into one definite state. Quantum Darwinism proposes that it's not about conscious observers, but about how the environment continuously measures quantum systems, filtering out fragile superpositions until only the most resilient information remains. Think of it like a radio tuning into a station. Only the strongest signals come through clearly, while the rest dissolve into static. Supporters argue this could finally explain why we don't see Schrödinger's cats dead and alive at the same time. The environment acts as a relentless editor, discarding quantum weirdness until only consistent classical facts are left. Critics, however, point out gaps like whether this process truly explains the uniqueness of our observed reality. Still, it's a compelling step toward reconciling quantum mechanics with our lived experience. As we ponder how reality emerges from quantum possibilities, another mystery beckons, one where particles seem to leave their own properties behind like a ghostly afterimage. But that's a story for next time. Now let's step into one of the strangest phenomena in quantum physics, where particles seem to leave their properties behind like a ghostly afterimage. This is the quantum Cheshire Cat effect, named after the vanishing feline from Alice in Wonderland. Here, particles appear to separate from their own characteristics in ways that defy classical intuition. Imagine a neutron, a tiny particle with properties like spin and position. In certain experiments, scientists have found that a neutron's spin can be detected in one place while its physical self is measured somewhere else entirely. It's as if the neutron's grin lingers long after the cat has disappeared, challenging our basic assumptions about how objects and their properties are connected. This bizarre behavior emerges from the principles of weak measurement, a technique that gently probes quantum systems without fully collapsing their states. By taking faint snapshots of a particle's journey, researchers can catch glimpses of its properties behaving independently, like a shadow detaching from its owner. The effect isn't just theoretical, it's been demonstrated in labs, proving that quantum mechanics allows for reality to fracture in ways we're still struggling to comprehend. What does this mean for the nature of reality? If properties like spin or momentum can exist apart from the particles they belong to, it suggests that the fabric of the universe might be far more fluid than we thought. Some interpretations argue this supports the idea that particles aren't solid objects but bundles of potentialities, with properties that can wander freely under the right conditions. Skeptics, however, caution that weak measurements might just reveal mathematical quirks rather than true physical separations. Whether the Cheshire Cat effect is a profound clue or a quantum mirage, it forces us to question whether reality is as concrete as it seems. And with that, we're ready to uncover another layer of the quantum world, one where biology itself might dance to the tune of the subatomic. Now let's take a surprising turn from the world of physics into the realm of living things, because quantum weirdness might not be confined to labs and particles. It could be at work inside plants, animals, and even our own bodies. This is quantum biology, where the rules of the subatomic world meet the complexity of life itself. Take photosynthesis, the process plants use to turn sunlight into energy. At first glance, it seems straightforward, but dig deeper and things get strange. Experiments suggest that photons of light don't just bounce randomly through a plant's cells. They might use quantum coherence to explore multiple paths at once, like a wave spreading out to find the most efficient route. This quantum-assisted efficiency could explain why plants convert sunlight so effectively, almost as if they've mastered a trick even our best solar panels haven't. Then there's bird navigation. Creatures like the European robin migrate thousands of miles with pinpoint accuracy, and the secret might lie in quantum entanglement. Scientists suspect that light-sensitive proteins in their eyes could exploit entangled electron pairs, acting like a microscopic compass tuned to Earth's magnetic field. If true, these birds aren't just following instincts, they're tapping into a quantum sense we're only beginning to understand. Even our sense of smell might have a quantum twist. The traditional theory says odor molecules fit into receptors like keys in locks, but some researchers argue vibrations within those molecules, governed by quantum tunneling, could be what our noses actually detect. It's a controversial idea, but if correct, every time you smell coffee or fresh rain, you're experiencing quantum mechanics in action. The big question is whether life evolved to harness these effects deliberately or if they're just accidental quirks. Supporters of quantum biology argue these phenomena are too precise to be coincidence, hinting that nature favors quantum tools for survival. Critics counter that warm, wet, and messy living cells should destroy fragile quantum states almost instantly. Whether life is inherently quantum or merely brushes against it, one thing's clear: the boundary between physics and biology is far blurrier than we ever imagined. And if these effects are real, they could revolutionize everything from medicine to energy. But for now, let's leave the living world and venture into an even deeper mystery: the quantum arrow of time, where the past, present, and future might not be as fixed as they seem. But here's something that might bend your mind even further. What if time itself is tangled up in quantum weirdness? Time feels like it moves in one direction, always pushing us forward, but quantum mechanics might have a different story to tell. In our everyday experience, time follows the second law of thermodynamics, the idea that disorder, or entropy, always increases. A shattered glass doesn't reassemble itself, and coffee cools instead of reheating. This gives us the familiar arrow of time, always pointing from past to future. But when we zoom into the quantum world, things get blurry. Quantum thermodynamics suggests that at the smallest scales, particles don't always play by these rules. Some quantum processes can appear reversible, meaning the distinction between past and future isn't as rigid. Experiments have even shown particles that seem to briefly retrace their steps as if flickering backward in time. It's not time travel in the sci-fi sense, but it does hint that the quantum arrow of time might not be as absolute as we think. The real puzzle is how these tiny, reversible quantum moments scale up into the irreversible flow of time we experience. One theory suggests that quantum decoherence, the same process that collapses superpositions, might lock in the forward direction of time as systems interact with their surroundings. Another idea ties time's arrow to the initial low entropy state of the early universe, a boundary condition that quantum fluctuations might have helped set in motion. What's fascinating is that this could rewrite our understanding of cause and effect. If quantum events aren't strictly bound to a one-way timeline, does that mean causality itself is flexible at some level? The debate is far from settled, but one thing certain: quantum mechanics forces us to rethink even the most fundamental aspects of reality, including the steady tick of time. Up next, we'll tackle another quantum head-scratcher. Does randomness rule the quantum world, or is there hidden order beneath the chaos? The answer might shake up everything we know about predictability in the universe. Now let's turn our attention to one of the most puzzling questions in quantum physics. Is the universe fundamentally random, or is there some hidden order we just can't see yet? At the heart of this mystery is the bizarre unpredictability of quantum events. Unlike a rolling dice where the outcome is chaotic but still governed by physical laws, quantum mechanics suggests that particles behave in ways that seem entirely random at their core. This idea didn't sit well with everyone, including Einstein, who famously declared, "God does not play dice with the universe." He and others proposed that maybe there were hidden variables, unknown factors that determine quantum behavior, making it only appear random. If we could uncover these hidden rules, the quantum world might snap into predictable order. That's where Bell's theorem comes in. In the 1960s, physicist John Bell devised a way to test whether hidden variables could explain quantum randomness. His theorem set up a series of mathematical inequalities that any hidden variable theory would have to obey. But when scientists ran experiments, most famously using entangled particles, quantum mechanics consistently violated these inequalities. The results suggested that no local hidden variables could fully explain the randomness we see. Later experiments closed loopholes that skeptics raised, making the case even stronger. The universe, it seems, really does embrace randomness at its most fundamental level. But here's the twist: some interpretations, like pilot wave theory, still argue for non-local hidden variables where influences can travel instantaneously across space. Others suggest that randomness might be an illusion caused by our limited perspective in a branching multiverse. So while the evidence leans heavily toward genuine quantum randomness, the debate isn't entirely settled. What does this mean for our understanding of reality? If the universe isn't just hiding its cards but truly dealing them at random, it reshapes everything from probability to free will. And speaking of reshaping reality, our next mystery takes this even further. Could every quantum decision be spawning entire new universes? The multiverse idea is up next, and it's as mind-bending as it sounds. Now let's dive into one of the most mind-expanding ideas in quantum physics, the multiverse. If you thought quantum randomness was strange, wait until you hear this. The many worlds interpretation suggests that every time a quantum particle makes a decision like whether to spin up or down, the universe splits into two, creating separate realities where each outcome happens. That means there could be countless versions of you living out every possible variation of every choice you've ever made. This idea came from physicist Hugh Everett in the 1950s, and it was his way of solving the measurement problem. Instead of a particle's wave function collapsing into a single state when observed, Everett proposed that all possible outcomes actually happen, just in different branching timelines. So in one universe, Schrödinger's cat is alive, in another, it's dead, and neither version is aware of the other. But here's where it gets even wilder. These branches aren't just limited to quantum particles. If the many worlds interpretation is correct, every tiny quantum event from the decay of an atom to the firing of a neuron in your brain could spawn new realities. That means there's a universe where you took that job offer, another where you never met your best friend, and maybe even one where dinosaurs never went extinct. Critics argue that the many worlds interpretation is untestable after all. How do you prove the existence of universes you can't see? But supporters counter that it's the simplest way to explain quantum mechanics without adding extra rules about wave function collapse. Plus, it removes the need for an observer to play a special role in shaping reality. Whether you find it thrilling or unsettling, the multiverse idea forces us to rethink what reality even means. If every possibility plays out somewhere, does that make our choices less meaningful? Or does it mean we're part of something far bigger than we ever imagined? And speaking of big ideas, our next mystery takes us even deeper into the question of whether consciousness itself might be shaping reality. That's coming up next. Now, let's venture into one of the most debated mysteries at the crossroads of quantum physics and philosophy: quantum consciousness. If the multiverse left you questioning reality, this idea might just flip everything on its head. The observer effect suggests that the act of measurement of simply observing a quantum system forces it to settle into a definite state. But here's the twist: some interpretations ask whether consciousness itself is the trigger. Could the mind be playing an active role in shaping reality? This idea isn't just science fiction. Physicists like John von Neumann and Eugene Wigner proposed that consciousness might be the missing link in quantum mechanics, the thing that collapses the wave function. In other words, without an observer, whether it's a human, an animal, or some other conscious entity, reality might remain in a blur of possibilities. Wigner even took it a step further with his famous Wigner's friend thought experiment, where two observers could, in theory, experience different outcomes of the same quantum event. What's fascinating is how eerily this mirrors ancient Eastern philosophies. For centuries, traditions like Buddhism and Hinduism have taught that consciousness is fundamental, that the world we perceive is shaped by our mind. The Upanishads, for example, describe reality as a projection of consciousness, not unlike how quantum mechanics suggests particles only choose a state when observed. Even the Taoist concept of the interconnectedness of all things finds a strange echo in quantum entanglement. But before we get too carried away, let's be clear, this is highly speculative. Mainstream physics still treats consciousness as an emergent property of the brain, not a cosmic architect. Critics argue that invoking consciousness to explain quantum mechanics risks veering into pseudoscience. After all, how do you test such an idea? Supporters, though, point out that the hard problem of consciousness, why we have subjective experience at all, remains unsolved, leaving room for radical possibilities. So, does consciousness create reality, or is it just another layer of the quantum mystery? Whether you lean toward the scientific or the philosophical, one thing's certain: the deeper we dig into quantum theory, the more it challenges our very notion of what's real. And that brings us to our next enigma, the invisible fabric underlying everything. We're about to explore how particles might just be ripples in something far more profound: quantum fields. Stay tuned. Now, let's peel back the curtain on something even more fundamental than particles: the quantum fields that make up the very fabric of reality. If particles are the characters in the story of the universe, quantum fields are the stage they perform on. Picture this: every particle you've ever heard of, electrons, quarks, even photons, aren't just tiny dots floating in empty space. They're ripples, tiny vibrations, in invisible fields that stretch across the entire cosmos. Think of these fields like an endless ocean where particles are the waves. An electron, for example, isn't just a solitary speck. It's a disturbance in the electron field. The same goes for every other particle in the standard model of physics, our best blueprint for how the universe works at its smallest scales. These fields aren't just abstract ideas, they're real, measurable, and they interact in precise ways. Now, here's where it gets even more intriguing. Some fields, like the Higgs field, don't just host particles, they give them mass. Imagine wading through a pool of syrup. The harder it is to move, the more mass you'd appear to have. That's essentially what the Higgs mechanism does. Particles interacting with the Higgs field slow down, and that resistance is what we perceive as mass. Without this field, electrons would zip around at light speed, atoms wouldn't hold together, and the universe as we know it wouldn't exist. What's wild is that these fields are never truly silent. Even in what we call a vacuum, fields are fizzing with activity, virtual particles popping in and out of existence, a quantum froth underpinning everything. This isn't just theoretical. We've detected the effects of these fluctuations in experiments like the Casimir effect, where invisible field interactions push objects together. So, when you look at the world around you, remember, what seems like solid matter is really a dance of excitations in an invisible, eternal field. And with that, we're ready to confront one of the biggest headaches in modern physics: why the energy of these fields doesn't add up the way we expect. That's next. Here's how we can dive into this next mystery. Imagine emptying out the universe, removing every star, every planet, even every stray atom. What's left? Not nothing, but a seething, bubbling quantum vacuum packed with energy. According to our best theories, this vacuum energy should be unimaginably powerful, shaping the very fate of the cosmos. But here's the problem: when we measure it, the energy we actually observe is almost zero. This enormous mismatch isn't just a small hiccup, it's one of the biggest unsolved problems in physics, and it threatens to unravel our understanding of the universe itself. So why does this matter? Think of it like this: vacuum energy isn't just background noise, it's tied to the expansion of the universe. Einstein first introduced the idea of a cosmological constant, a sort of anti-gravity pushing space apart. Later, quantum physics suggested this constant should come from vacuum energy. But here's where things break down when physicists calculate how much energy the quantum fields in empty space should contribute. The numbers are mind-boggling. We're talking about a discrepancy of 1 followed by 120 zeros. That's so enormous that if the math were correct, the universe would have torn itself apart before galaxies could even form. So why don't we see that? Either our calculations are missing something fundamental, or there's a hidden mechanism canceling out nearly all this energy. Some theories suggest unknown symmetries in nature balance the books, while others propose entirely new physics beyond the standard model. But until we solve this, our models of cosmology rest on shaky ground. After all, if we can't explain the energy of empty space, how well do we really understand the universe? And this isn't just a theoretical puzzle, it has real consequences. The tiny bit of vacuum energy we do detect might be what's accelerating the expansion of the universe, the so-called dark energy. But why is it so weak compared to predictions? That's the quantum vacuum catastrophe, a glaring gap in our knowledge that keeps physicists up at night. Now, as we grapple with this cosmic discrepancy, another mystery looms, one that questions whether reality itself could be non-local. But that's a story for next time. But speaking of mysteries that challenge our very understanding of reality, let's turn our attention to quantum non-locality. If you thought entangled particles acting in sync was strange, wait until you hear just how deeply this phenomenon upends the classic notion of locality, the idea that objects can only be influenced by their immediate surroundings. In the quantum world, particles that have once been linked continue to affect each other instantaneously, no matter how far apart they are. Einstein famously called this spooky action at a distance, because it defies the speed of light, the cosmic speed limit set by his own theory of relativity. Recent experiments have taken this strangeness to a whole new level. scientists have now conducted loophole-free tests closing every possible gap that skeptics might point to. The results, entanglement holds up, even when particles are separated by hundreds of kilometers. Measuring one instantly determines the state of its partner faster than light could ever travel between them. This isn't just a quirk, it's a fundamental feature of reality, forcing us to rethink how information and influence can spread. What makes this so revolutionary? Well, if effects can propagate without passing through the space in between, then distance and separation might not be what we think they are. Some theories suggest that non-locality implies a deeper, hidden layer of connectivity in the universe where space itself emerges from quantum relationships. Others speculate it could pave the way for ultra-secure quantum communication networks where messages are transmitted with perfect privacy. The implications don't stop there. If particles can influence each other beyond space and time, could this hint at a universe where the very fabric of reality is woven together by quantum threads we don't yet understand? It's a question that takes us to the edge of modern physics and possibly beyond. And with that, we're left staring at yet another quantum enigma, one that pushes the boundaries of what we think is possible. Now, let's take a mind-bending leap into one of the most provocative ideas in modern physics: quantum simulated reality. If the universe operates like an ultra-advanced quantum computer, could everything we see, feel, and experience just be lines of code in a cosmic program? This isn't science fiction anymore. Some physicists argue that the very quirks of quantum mechanics might be clues pointing to a simulated universe. Think about it. In video games, complex simulations only render details when a player is looking at them, similar to how quantum particles collapse into definite states only when observed. The uncertainty principle, superposition, even entanglement, these could all be signs of processing limits or optimization tricks in a grand simulation. Just as a computer approximates physics to save resources, maybe quantum weirdness is the universe's way of conserving computational power. But here's where it gets even wilder. If reality is a simulation, who's running it? Are we the accidental creations of some higher dimensional programmer, or are we ourselves simulations within simulations, nested like digital Russian dolls? And if the universe is a quantum program, could we ever hack it? Some theorists suggest that manipulating quantum systems might one day let us glimpse the source code of reality itself. Of course, not everyone's convinced. Critics say the simulation hypothesis is untestable, more philosophy than physics. But with quantum tech advancing, we might someday find glitches in the matrix, like anomalies in particle behavior or patterns in cosmic background radiation. Whether you buy into the idea or not, it forces us to ask profound questions. What is real? And if the universe is a simulation, does that make it any less meaningful? As we wrestle with these possibilities, one thing's certain: quantum mechanics keeps blurring the line between science and the surreal. And that brings us to our next mystery, where quantum theory collides with one of existence's biggest puzzles. Now, let's venture into one of the most haunting questions of all: what happens to consciousness when we die? Quantum physics might have a wild answer. Picture this: according to the many worlds interpretation, every possible outcome of a quantum event spawns a new universe. So what if death isn't the end, but just a branching point? This idea, called quantum immortality, suggests your consciousness could keep shifting into realities where you survive, forever skirting death in an infinite multiverse. But here's where things get eerie. Some researchers tie this to near-death experiences, those vivid reports of tunnels of light or out-of-body sensations. Could these moments be glimpses into alternate quantum realities, or maybe flashes of consciousness decoupling from the physical brain? Theories range from quantum vibrations in microtubules, tiny structures in our neurons, to the idea that awareness itself is a fundamental force of nature like gravity. Of course, this is speculative territory. critics argue there's no evidence consciousness survives death, and quantum effects in the brain remain hotly debated. But the sheer possibility forces us to rethink life's biggest mystery. If consciousness is woven into the fabric of reality, could death just be a door to another quantum state? Whether you find this comforting or unsettling, one thing's clear: quantum physics keeps pushing the boundaries of what we consider possible. And as we near the end of our journey, that brings us to the ultimate frontier, the quest for a theory that ties it all together. Taking a step beyond these mind-bending possibilities, we arrive at the final frontier in our quantum journey, the grand unified theory. This is the holy grail of physics, the dream of merging quantum mechanics with the other fundamental forces of nature into one elegant framework. Think of it as the ultimate puzzle where gravity, electromagnetism, and the nuclear forces all snap into place under a single set of rules. Right now, our understanding of the universe is split. Quantum mechanics reigns supreme in the tiny world of particles, while Einstein's general relativity governs the vast cosmos. But when these two theories collide, like near black holes or at the Big Bang, the math breaks down completely. That's where the grand unified theory comes in. Whether it's string theories, vibrating filaments, loop quantum gravities, woven space-time, or something entirely new, the goal is the same: to explain reality at every scale, from the quantum foam to the expanding universe. What makes this so thrilling? Solving it wouldn't just fill textbooks, it could rewrite them. Imagine unlocking the quantum code of gravity, revealing hidden dimensions, or even discovering what happened before the Big Bang. Every mystery we've explored, entanglement, superposition, even consciousness, might suddenly click into a grander picture. Of course, the path is littered with challenges. Some theories require 10 dimensions we can't see. Others predict particles we've never detected. But each dead end teaches us something new. And if history's any guide, the breakthroughs will come from the very quantum weirdness that baffles us today. So as we close this exploration, remember, these 30 mysteries aren't just curiosities. They're pieces of a cosmic riddle waiting to be solved. And when that final piece falls into place, our understanding of reality might just take a quantum leap. If you've enjoyed this deep dive into the universe's greatest puzzles, don't forget to subscribe for more mind-expanding journeys. The quantum world is strange, but the adventure is just beginning. Drop your wildest theories in the comments below. What do you think holds the key to unifying physics? And with that, we've journeyed through the 30 most profound quantum mysteries that could hold the keys to unraveling the universe itself. From the bizarre duality of particles to the spooky connections of entanglement, from the mind-bending possibilities of the multiverse to the elusive dream of a grand unified theory, each mystery peels back another layer of reality's deepest secrets. Together, they paint a picture of a cosmos far stranger and more interconnected than we ever imagined. What's truly remarkable is how these puzzles aren't just isolated curiosities, they're threads in a grand tapestry. Solving one could unlock breakthroughs in others, revealing a unified understanding of everything from the smallest quantum flutter to the vast expanse of space-time. Whether it's harnessing entanglement for instant communication, tapping into vacuum energy, or even redefining what it means to be conscious, the implications are limitless. But here's the best part: this isn't just a story for physicists. It's an invitation to all of us to stay curious, to question, and to wonder. Because somewhere in these mysteries lies the next revolution in science, and it might just start with an idea from someone like you. If this dive into the quantum unknown left you hungry for more, don't forget to hit that subscribe button and ring the bell. You won't want to miss the next mind-bending adventure. And drop a comment below: which of these quantum mysteries fascinates you the most? Do you think we're closer to solving them than we realize, or is the universe always one step ahead? Let's keep the conversation going, because the universe's greatest secrets are still out there, waiting to be uncovered. Until next time, stay curious and keep exploring.